Welcome aboard, space crew. Today's mission takes us deep into the mysteries of the universe. So hold on tight as we blast off into the stars.
Time. It always feels like it's moving forward. But the universe shows us that it's much more complex. Time can slow, stretch, freeze, even reverse. Some of physics' most fundamental equations don't even care about the past or future at all. So why does time feel so brutally linear to us? And if time itself began at the Big Bang, what happens when you follow it all the way back to the moment before it even existed? Here are 15 space facts that prove time is broken. Number 15. Astronauts age slower. When humans leave Earth and orbit the planet aboard the International Space Station, time treats them differently. Because they're moving extremely fast, about 28,000 kilometers per hour, time slows down for them. This comes from Einstein's special relativity, which says the faster you move through space, the slower you move through time. There's also gravity involved. Earth's gravity pulls time down with it. The weaker the gravity, the faster time flows. Astronauts are higher up, feeling less gravity, so their clocks tick a little faster for that reason too. Speed slows their time. Weaker gravity speeds it up. That's why they age milliseconds less than people on Earth. Their bodies, their atoms, their biological clocks, all slightly out of sync with ours. This is the famous twin paradox, but it's no longer a thought experiment. We've measured it. Humans have lived it. But then, if time can slow down for astronauts just by moving fast and changing altitude, is now really the same everywhere on Earth? Or are we all living in slightly different versions of the present? Number 14. Time slows in flight. Time doesn't just change in space, it changes on different heights. In 1971, physicists decided to test a strange idea. They took incredibly precise atomic clocks, put them on commercial airplanes, and flew them around the Earth. Other identical clocks stayed on the ground. When the flights ended, they compared the clocks. They didn't match. The clocks in the air had drifted by tiny but measurable amounts, exactly the amount Einstein's equations predicted. This became known as the Hafele-Keating experiment, and it proved something unsettling. Time wasn't just passing differently, it was disagreeing with itself. Planes basically move faster than the Earth's surface, which slows time down because of speed. But planes are also higher up, where gravity is slightly weaker, which speeds time up. Depending on the direction the plane flew, one effect won over the other, and the clocks told the story with brutal honesty. Planes show tiny differences, but what about stationary points on Earth? Can mere elevation bend time? Number 13. Mountains beat the clock. Gravity doesn't just keep your feet on the ground, it controls how fast time moves. The stronger the gravity, the slower time passes. The weaker the gravity, the faster it flows. This is called gravitational time dilation, and it's not subtle. Clocks placed on mountaintops tick slightly faster than clocks at sea level. The difference is only nanoseconds, but it's real. So real that modern atomic clocks can measure it over just a few kilometers of height. Higher up means weaker gravity. Weaker gravity means faster time. GPS satellites rely on this effect. If engineers ignored it, your location would drift by kilometers every single day. Navigation would quietly fall apart. So two clocks, perfectly synchronized, placed at different elevations, will slowly fall out of agreement just because gravity treats them differently. That means now on a mountain isn't quite the same now at sea level. But if gravity can change time on a mountain, what happens to it near something truly massive? Number 12. Gravity warps time. Einstein taught us to think of the universe as spacetime, a four-dimensional fabric that can bend and stretch. Massive objects, like planets and stars, curve this fabric, and time is stitched right into it. The stronger the curve, the slower time ticks. So near a black hole, or even a very dense star, it stretches and slows in ways that feel impossible. Gravity is the geometry those clocks move through. Time is bending because space-time bends. If gravity can warp time, can it influence the technology we rely on every day? Number 11. Satellites fight time drift. GPS satellites orbit high above Earth, moving at tremendous speeds and experiencing weaker gravity than we do on the surface. Because motion slows time and weaker gravity speeds it up, the clocks aboard these satellites tick at a different rate than clocks on the ground. By itself, a difference of just 38 microseconds per day might sound tiny, but GPS systems measure positions down to meters. Without correcting for this time drift, your phone could send you kilometers off course, maybe right into a lake instead of the coffee shop. Satellites are literally orbiting Earth. They're constantly fighting with time itself, keeping the universe's messy clocks in check. Satellites adjust for tiny differences, but what about the extreme limit of gravity, where time itself seems to stop? Number 10. Time freezes at horizons. Black holes are the ultimate time machines, in reverse. Imagine two people, one floating at a safe distance, watching a black hole, and the other daring to fall in. As the second person approaches the event horizon, the point of no return. To the distant observer, time for the falling person seems to slow down, then almost freeze. Light from them stretches into red, then infrared, fading away into nothing. This is called gravitational redshift, and this is how space-time behaves near extreme gravity. But for the person falling in, time flows normally. Seconds tick by, just like anywhere else. Two observers, two realities, and two very different experiences of now. If time can freeze or slow depending on gravity, what about the laws of physics themselves? Number 9. Equations ignore directions. The fundamental laws of physics don't care about time at all. Take Newton's laws, Maxwell's equations for electricity and magnetism, or even the Schrödinger equation in quantum mechanics. They work just as well if you run time backward. Particles would move, forces would act, waves would propagate. Everything would still make perfect sense. Time has no built-in direction in these equations. It's like the universe wrote a script that could be played forward or backward without breaking a scene. But we don't experience time that way. We remember the past, not the future. Moments happen, but don't unhappen. Then if the laws themselves don't know which way time flows, where does the direction of past to future come from? Number 8. Entropy sets time's arrow. Entropy, the second law of thermodynamics, says that in a closed system, disorder tends to increase. It's just probability. There are far more ways for things to be messy than neat, and that imbalance points time forward. Think of it like a deck of cards. Shuffle once, shuffle twice, shuffle a million times. Eventually, everything ends up messy. That's how entropy works. So the reason we remember the past but not the future is just statistics. The universe likes to go from order to disorder, and we follow along. If entropy defines the present, was it always like this? Did time tick the same in the early universe? Number 7. A younger universe clock. Time as we know it didn't always tick the same way. In the early universe, everything was hotter, denser, and more chaotic than we can imagine. At that moment, time evolved. The flow of seconds, minutes, and hours depended on the universe itself cooling and expanding. As the cosmos spread out, entropy began to rise, setting the direction of time we feel today. The clocks of the universe were literally being built as space expanded. Early moments were extreme, conditions so intense that conventional time, like we experience it, barely existed. But if time itself needed the universe to cool and stretch before it could tick normally, what did before even mean? What existed before time began moving at all? This is mission control. Temporal stability has dropped below safe limits. The ship's clocks have desynchronized. Subscribe now to anchor yourself to this moment, because the timeline ahead is unstable and there may be no return to the present. Number 6. Effects before causes. Quantum mechanics has a way of breaking our common sense. In some experiments, like the delayed choice experiment, particles behave as if they know what will be measured in the future. Measuring them now can influence how they acted earlier. It doesn't break physics, and it's just that causality gets fuzzy at the quantum level. Particles are connected through correlations we can't see. The act of measurement itself can redefine their history, creating effects that seem to precede their causes. Then, if the outcome depends on future measurements, is time itself making the decision? Are the past and future more entangled than we realize? Number 5. Time from entanglement. Some physicists think time is emergent. It only appears because of relationships between quantum particles. In the Page-Wooders mechanism, entangled particles act like tiny clocks. Their correlations create the sense of one event happening before another. Without those relationships, the universe wouldn't have a before or after at all. It's like time is less a river flowing and more a dance between particles, a rhythm created by connection rather than by anything fundamental. If time emerges from relationships, what happens when experiments seem to defy it entirely? Number 4. Particles that ran early. In 2011, the physics world held its breath. The opera experiment in Italy seemed to show neutrinos traveling faster than light. Faster than light? That's a cosmic no-no. According to Einstein, nothing, not even tiny particles, can outrun light. Headlines exploded. Could time limits themselves be broken? Physicists double-checked everything, triple-checked everything, and finally found the culprit: a loose fiber optic cable. A tiny technical glitch had created a cosmic illusion. Time itself wasn't violated. The laws of physics were safe, but our certainty completely shattered. Even the smartest labs in the world can be fooled by something as small as a loose wire. Sometimes science is about correcting itself, catching our mistakes, and letting reality speak. Number 3. Loops hidden in space. Einstein's equations allow something called closed time-like curves, paths through spacetime that loop back on themselves. In theory, you could travel along one and return to your own past. Kurt Gödel even described a universe where these loops were possible. But when you try to make them real, physics pushes back. Energy conditions, stability problems, quantum effects, they all conspire to keep these loops from actually happening. Nature seems to have rules that mathematics alone doesn't account for. If equations let time fold back on itself, but reality forbids it, then what exactly is enforcing the universe's limits? Number 2. Time is emergent. Some theories in quantum gravity suggest that at the tiniest scales, near the Planck length, space and time themselves might dissolve. At that level, the universe doesn't have a built-in clock ticking forward. Time might emerge only as a byproduct of deeper physical processes, like temperature emerging from countless particles moving around. It's as if time is real, but only because of everything else happening in the universe. Take away the interactions, the entanglements, the structure, and time might vanish entirely. Time exists the way waves exist in the ocean, real, tangible, but dependent on the medium. So the seconds we count, the minutes we measure, the years we live, they might not be fundamental parts of reality. Time could simply be the universe keeping track of itself, emerging from the dance of matter, energy, and quantum connections. But if time emerges, bends, and stretches, what about the very beginning? Did time exist at all before the Big Bang? Number 1. Before time began. The very beginning of time. The Big Bang wasn't just the start of the universe, it was the start of time itself. Asking what came before is meaningless because there was no before. Time, as we know it, only began when space began to expand. Stephen Hawking's no-boundary proposal even suggests that the universe had no edge or starting point in the traditional sense. Time itself was part of the fabric that emerged from the very beginning. This explains why time feels so linear to us. Our experience is tied to the direction of entropy and the expanding cosmos. Physics doesn't care about the past or the future, it just is. And yet humans must perceive time as a flowing sequence, because that's how we navigate, remember, and imagine. But what do you think? Is time really relative, or is it something the human mind will never truly comprehend? Drop your thoughts in the comments below. Until our next mission, keep your eyes on the stars.
Our mission is complete, and we're coming in for landing. Stay aboard and join the crew again as we continue unveiling the stars.